Hello students, in this lecture we will read about potential energy of a system of charges. Here, to understand how we are deriving the potential energy for the given charges, we will start with a very simple system. The simple system consists of only two charges. Then we will try to find potential energy for a three-charge system. And for additional help I will derive a four-charge system and similarly will explain n number of systems in this lecture. So we will understand how these charges are playing important role, how their distances are playing important role, and initially from where these charges are coming and how we are making them bind together in a particular system. So let's start with the class. So let us consider the two charges Q1 and Q2 with position vectors R1 and R2. We are considering two charges Q1 and Q2 for our two-charge system. Now this Q1 and Q2 are kept apart at a distance of some R. As this is Q1 and this is Q2, we name for our convenience this distance as R12. Initially these charges were not present in this configuration. We have brought them to this configuration. For doing so, we will consider that our charges Q1 and Q2 were present at infinity to each other. They were not together at infinity also. One was in x-axis infinity, one was in plus y-axis, or maybe one in z minus or one in z plus. So anywhere, but they were not together. They were at some position apart and at infinity. Now what we are aiming to do is that from this infinity 1 we are bringing charge Q1 to here, and from this infinity 2 we are bringing charge Q to this point. So exactly what happens over here is to bring the charge from infinity to here, to bring Q1 from here to here, there is no work done. Why there is no work done? Because there is no charge present in this system. There is no resistance for movement of charge Q1. There is no potential, no external phase. So our charge Q1 is free to move in this particular system unless until we are introducing another charge, that is Q2, in this system. So first we brought our charge Q1 from infinity, which do not need any sort of work to be done on it. It was simple, easy to access and easy to move. Now next what we are doing is that from infinity to we are bringing our charge Q2, and to bring that charge Q2 we will see that we need to do some work. Work done over here is 0. Now to bring this charge Q2 over here, we need to do some work. Work is to be done. And why this work is to be done? For Q1 we did not do. Why for Q2? Because there is some potential arising due to Q1 which will repel or attract Q2. On the basis of the charge held by Q2. Repel or attract. If Q2 is of opposite polarity to Q1, they will show attraction. If Q2 is of the same polarity as of Q1, they will repel. So to bring these two in this configuration of distance R1/2, we aim to provide some external work, and that work, how we are going to find, will be studied in this particular part. So hopefully you understood the basics, how we are bringing and how we are defining it. You got to know work done for Q1 is 0, and for bringing Q2 we need to do some work. Now let's start up with this. Let us calculate work done externally to build up the configuration of two charges. We initially consider the charges q1 and q2 at infinity and determine the work done by an external agency to bring the charges to the given location. Suppose first the charge q1 is brought from infinity to the point r1. There is no external field against which work needs to be done. So work done in bringing the q1 from infinity is 0. From infinity to r1 is 0. So this charge produces a potential in this space given by V1 equals to 1 by 4 pi epsilon naught into Q1 by R1P. So this is the potential which is being produced by charge Q1 in the space where this charge Q1 is brought from the infinity. Q1 is brought from the infinity. Now this distance R1P is distance from the point P in the space to the location of Q1. So P is a distance at infinity, From infinity to this particular distance of R we are bringing. To this particular distance of R1 we are bringing it. This distance is R2. So that distance we define for our convenience as R1P. Okay. From the definition of potential, work done in bringing the charge Q2 from infinity to the point R2 is Q2 times the potential at R2 due to Q1. So there is some potential due to Q1, some potential V, and work done is how much thing you want to bring in this particular potential. So Q2 is the charge which needs to invade this particular potential. Q2 is the charge which will be invading this particular potential. So work done will be the product of our charge which is invading the given potential. So work done for bringing Q2 will be V due to charge 1 into Q2. And from this equation number 1, we have seen that V1 equals to 1 by 4 pi epsilon naught into Q1 upon R1. And the potential which is extending from Q1 to Q2 will be covering a distance of R12. Hence this will be changed. We are not going to take R1P. That is for considering the potential from infinity to point R1. Now we are considering the potential due to 1 from Q1 to Q2. So the distance from Q1 to Q2 is R12. That is what distance we need to consider. Okay. So the work done on Q2 is given as W equals to 1 by 4 pi epsilon naught into Q1 into Q2 by R12. Work done when bringing charge Q1 with 0. Work done to bring charge Q2 is K Q1 Q2 upon R12. And this R12 is defined as the distance between the point 1 and 2. Distance between the point 1 and 2. So we have got the work done for our system where we have considered only two charges. Both the charges are coming from infinity and one charge is being placed at R1 and the other charge is being placed at R2. So the distance between charge 1 and charge 2 comes around R12. Moving on. Since electrostatic force is conservative, we have read it's conservative. This work gets stored in the form of potential energy of system because we need to conserve this force. So this force will neither be created nor be destroyed but will be stored as some other form. So the other form which it's been stored is in the form of potential energy of that system. Potential energy of system. This potential energy helps the system to maintain its configuration too, because if these charges are going apart, they are not been in the configuration, the potential energy will be changed. If they are coming nearer, again the potential energy will change. So these changes of the potential energy will disbalance the whole system and the configuration will not be maintained. So in a way we can say the stored potential energy of the system helps in maintaining the configuration, helps in maintaining the configuration of given system. Now potential energy thus stored in the system of two charges Q1 and Q2 is given by U equals to 1 by 4 pi epsilon naught into Q1 Q2 by R12. That is the amount of work done. That is equal to the amount of work done. Amount of work done. Now generally the potential energy would be unaltered when whatever may be the charges that are brought at the specified location because of path independence of work for electrostatic forces. Now what exactly this want to say is that this potential energy will not differ. This potential energy will not differ in case we are bringing charge Q1 later than Q2. Charge Q2 is brought before charge Q1 because this potential energy does not depend upon the path followed, does not depend upon the path that is being followed. Instead, what it depends upon is the configuration, the last resultant configuration of the system. That is what our potential energy depends upon. So this particular statement, the no change in the energy of these two systems gives us the proof, the validation of the fact that potential energy and the work done are path independent, This proves it. Now in this particular formula we have defined potential energy and amount of work done for the two charge system. Now we will try for the three charges, but before that let's understand if Q1 and Q2 have different sorts of polarity. Now what exactly we do have is we have a charge Q1 and a charge Q2. These charges can be positive, can be negative. A charge Q1 can be positive, can be negative, whereas charge Q2 also have property to be a positive charge or be a negative charge. So like the potential which we will be defining is directly proportional to the product of Q1 and Q2. We aim at Q1 and Q2 being the like charges. We assume that Q1 and Q2 are like charges. So what will be the polarity of potential? Potential will be positive. Now in the second case we aim that Q1 and Q2 are unlike charges. So what will be the polarity of our potential energy? It will be negative. Now understand how Q1 and Q2 if are like it's positive and how if not are negative. To understand this, just see, if our Q1 is same as Q2, this is not equal, take this sign here as, same in the polarity, same as, then both will either be negative or be positive. So Q1 positive into positive Q2, what will they give you? Positive Q1 Q2. Negative Q1 into negative Q2, what will they give you? Negative will turn into positive when we go for product and it will give positive Q1 Q2. So in both the cases when the charges Q1 and Q2 are the like charges, we get potential energy positive, and When these are unlike charges, one positive charge, one negative charge, and we are taking the product of both the charges, answer of the product will be negative. Now, in case we are getting potential energy positive, that means our charges are like charges. What is the property of like charges? Like charges repel each other, repulsive in nature, and when they are unlike charges, they will attract. That is the basic property of charges we have read in the chapter 1 in the section 1 itself. Attractive in nature. Now, they are repulsive. They will try to move apart. They will try to move apart. So, what we aim to do is, we aim to do work on the system to bring them near, to bring them in the configuration, in bringing them to configuration. Whereas these are attractive, so they will try to attract. Then internally we have to provide some work to this system to bring them apart in the configuration. Bring apart to maintain the configuration. In both the cases, we aim at maintaining the configuration. For one case, it's attractive, so we need to pull them apart. On the other case, they are repulsive, so we need to pull them nearer. So, this is how the configuration needs to be maintained. We'll go through the points given over here. Above equation is true for any sign of Q1 and Q2. If Q1 and Q2 are greater than 0, that implies positive. Potential energy is positive. Since for like charges, Q1 into Q2 is greater than 0, electrostatic forces is repulsive, and a positive amount of work is needed to be done against these forces to bring the charges from infinity to a finite distance apart. We need to do positive amount of work. This is very much important. When potential is positive, work done is positive. When potential is positive, work done is positive. And this happens in the case of the product of Q1, Q2 being positive or greater than 0. Now, for unlike charges Q1, Q2 being smaller than 0, that is negative, the electrostatic forces are attractive. The forces between the two charges are attractive. Positive amount of work is needed against this force to take the charges from the given location to infinity. In the previous case, we were talking to bring the charges nearer. Here we are talking to bring them apart. Bring them apart. In other words, a negative amount of work is needed for the reverse path from infinity to the present location. We have to provide an negative amount of work to the system to bring the charge Q2 from infinity to point R2. Now let's understand this statement clearly. What it aims at saying is that negative amount of work, we have to do the work against the attractive forces of the two charges. See, we are having a north pole and a south pole. If we are bringing them at a defined distance of r, what will happen? They will attract and try to reduce this distance of r. So let me draw it for you to make it more easy and more understandable. See, over here we are having this one part of a magnet. This is north and this is another part of magnet. This is south. They are kept at one distance of r. Now at this distance it starts attracting. It starts attracting the south, and this south starts attracting the north. What will happen? In the attraction they will move nearer. In the attraction, movement will happen and they will start moving near to each other. Now we need to work against this movement. We need to work against this attractive movement. So our work done is taken to be negative in this case. We need to work against this attractive movement to keep these two charges at the defined position of R1 and R2. That's how the work done over here is negative work. Hopefully you understood how we took positive work and the negative work. We'll move to the next. So above we have seen the equation where we have found out work done for two system charges, two charge system, and we get to know that the work done for the two charge system is equal to K into Q1 Q2 upon R12. Now this is a generalized form and this generalized form can be used for n number of point charges. Now we will aim at calculating for the three charge system. So in this case what exactly we had is three charges Q1, Q2, Q3, and in the similar way the way we have taken charge Q1, charge Q2, charge Q3, like in the previous system we have taken charge Q1 and charge Q2. Similarly we will take Q1, Q2 and Q3 from the infinity. Again we assume that we have three charges Q1, Q2, Q3 initially at infinity, then finally they are brought in a configuration of R1, then the other one brought at R12 and the third one is brought at R123. Why I am writing it as R123 and R1 R12? Because first we have brought it to a position R1. Now the Q2 will be brought with respect to R1 and this Q3 will be brought with respect to R1 as well as with respect to R2. That's why, just to define it in a proper, easy, understandable way, I am writing it in this way. Now we'll go through. Let's calculate the potential energy of a system of three charges Q1, Q2 and Q3 located at a distance of R1 vector, R2 vector, R3 vector respectively. To bring the Q1 first from infinity to R1, no work is required. Next we bring Q2 from infinity to position R2. The work done here is equal to the amount Q2 into potential due to 1. So let me explain it in a proper way. First of all, what exactly do we have is three charges and they need to be brought in this particular given configuration. And to bring first charge, Q1 is not charge Q1 but it is the first charge to be brought into the system. Any charge which is brought into the system for the first when there is no other charge existing, the work done is 0 because there is no potential to repel or attract the charge. So there is no work done. But next when we are bringing Q2 and Q3, there will be some work we need to do. We need to provide into the system to maintain the given configuration. Now for bringing the charge Q2 to R2 position, we need to do an amount of work which is equal to the charge into potential due to 1. The potential which can be repulsive in nature, which can be attractive in nature. Okay. So Q2 into the potential due to 1 at position R. I will write over here what does Q2 V1 R2 implies. It implies product of potential due to Q1 at R2 and charge Q2. Q2 V1 of R2, product of potential. This thing is here, a product sign is there. Product of potential due to Q1, where? At R2, not at R1, at R2, and the charge Q2. This is only for product, and this particular value V1 R2 implies potential due to charge 1 at R2. Hopefully you got it. Now we brought our charge Q3 in the system. Now in this system we have charge Q1, we have charge Q2. So to define it, we will have Q3 into potential due to 1 at R3 plus potential due to 2 at R3. Both the charges will have some amount of potential. See, this will give you some potential like this in this direction, and this charge will give you some potential like this in this direction. So both will have equal effect on Q3. Both will have equal effect on Q3. Okay, so see, the charges Q1 and Q2 produce a potential which at any point P is given by V1 2 equals to 1 by 4 pi epsilon naught into Q1 by R1P plus Q2 by R2P. Work done next in bringing Q3 from infinity to the point R3 is given by Q3 times V at 1, V at 2 at R3. V at 2 at R3. So we have merged this V and this V into one V1 2. So potential due to 1 position 1 or charge 1 and potential due to charge 2, both are merged into single. Now product of Q3 into V12 into R3 equals to 1 by 4 pi epsilon naught, and as we have seen V1, 2 is this, V1, like V1, 2 is this particular, and in this we have multiplied it with Q3 to get this particular equation. Now we have got Q1 into Q3 by R1 R3 plus Q2 into Q3 by R23. This is the location from 1 to 3, from 2 to 3. The total work done is assembling the charges at a given location is obtained by adding the work done in different steps. Now we add the work. The total work done is step 1, step 2 and step 3. First, work done when we brought charge Q1, then work done to bring charge Q2, then work done to bring charge Q3. All will be summed up to get the total work done to maintain that particular configuration of 3 charges system. So we will add this equation. Work done due to 1 was 0. For 2 it was given with this equation, and for 3 it is given with this equation. So we will add it up and we get that potential energy is given by 1 by 4 pi epsilon naught into Q1 Q2 by R1 2 plus Q1 Q3 by R13 plus Q2 Q3 by R23. The potential energy is characteristic of the present state of configuration and not the way the state is achieved. This statement over here clearly says that if we are bringing charge Q3 in the system before charge Q1 and Q2, still we will get the same answer. In case we are bringing charge Q2 before Q1 and Q3, still the answer will be same. And if we are bringing any other 3 charges from infinity to this particular point, the formula given for the potential energy, the amount of work done, the amount of potential energy for the system will remain same. It will not change because our potential energy depends upon the configuration at present. But in case we are changing the magnitude of charge, we are changing the distance between the given charges, it will definitely affect the potential energy as per to the relation. More the distance, less will be the potential. Less will be the distance, more will be the potential. magnitude of charges increased will increase the potential, and decrease in the magnitude of charges will definitely decrease the potential. So these are the things. We will just go through a whole thing what we have read in this lecture. Just we'll get a short summary of it. Firstly, we have read about the two charge system, and the second we read about three charge system. In this two charge system, we have got charge Q1 and Q2 from infinity to a distance of R12, and in this we have got three charges from infinity to this particular configuration of charges, as this distance R13, R12, R23. So these were the charges we have got from infinity. Now what exactly we did, we brought this one, will take as R1 position vector, R2 position vector, R1 position vector, R2 position vector, and R3 position vector, right? From infinity we have got all the charges Q1, Q2 and in this case here Q1, Q2 and Q3. In the first case only two charges, and in the second case we got three charges. So Q1 was brought to R1 and Q2 was brought to R2. Here no other charge was present, no other charge present. Hence work done equals to 0. Q1 present. So as per to the definition, work done equals to Q2 into potential energy due to 1 at R2 position vector. So work done we received as Q2, I'll just write over here again, work done was equals to K Q1 Q2 upon R12. From where does all this came? Because the potential due to Q1 was given as K Q1 upon R1 P. Okay, we have taken infinity at P, that so that we can define it by some alphabetical word. Now here it is 0, here it is this. In both the step we have done this process in step 1 and step 2. Now total work done equals to work done in step 1 plus work done in step 2. In step 1 work done is 0, and in step 2 work done is KQ1 Q2 upon R12. Hence the total work done is KQ1 Q2 upon R12. So that's how we have derived for two charges. Now we will define for the given three charges. Okay, this particular. Now Q1 is brought from infinity to R1, Q2 brought from infinity to R2, Q3 brought from infinity to R3. Now in case of this, no work is done because no extra charge present, no charge in space was there. In case of this, Q2 amount of work done equals to Q2 into V at V due to charge 1 at position vector of R2. Why so? Because at R1 position Q1 was present. Now what is the value of V1? It is equals to KQ1 upon R1P, because the charge 1 is brought from the infinity to this particular point of R1. Now we will define Q3. For Q3 with the greening to distinguish well, W equals to Q 3 into V1 at R3 plus V2 at R3. This is potential due to 1, potential due to 2. So the potential at R3 will be like potential due to charge 2 is given as KQ2 upon R2P. This R like distance from infinity to position vector of 2. This is the potential due to charge 2. So it will come Q3 into potential due to 1 is given as KQ1 upon R13 at position 3 we are asking. So it is 13 plus KQ2 upon R23 from 2 to position 3. So after making the common out and charges together, the value we received is K into Q1 Q3 upon R13 plus Q2 Q3 upon R23. So this is the amount of work done for bringing charge 3 to the position of R3. This one step was not clearly elaborately written in the notes, so make a note of it. Now we will go on the last step. The last step for the three charge system is to find the total work done. Total work done, that is work done in step 1 plus work done in step 2 plus work done in step 3. In step 1 it is 0. In this it is Q2 V1 at R2, and for this it is Q3 at V1 R3 plus V2 at R3. So the total work comes about WT equals to Q2 V1 at R2 plus Q3 into V1 at R3 plus V2 at R3. Now we know it is equals to KQ1 Q2 upon R12 plus this one is K into Q2 Q3 upon R23 plus Q1 Q3 upon R13. Now here also we see that this K and this K are common. Taking the common out, work total done equals to K into Q1 Q2 upon R12 plus Q2 Q3 into R1 divided by R23 plus Q1 Q3 upon R13. So that is how we have found out the total work done. Now I'll just explain you a very simple case of 4 charges in this system. Very fastly we will go through it just to give you a little extra idea to make the concept little more clear. We are having charges Q1, Q2, Q3 and Q4 brought in a configuration. So as these are 4 charges, mostly the configuration which will come is about the square configuration or the rectangular configuration or any kind of quadrilateral configuration we can assume. Quadrilateral. So basically what we aim to know in this quadrilateral is the distance r from 1 to 2, from 2 to 3, from 3 to 4 and from 4 to 1 again. So in case we are defining it as a square, all the distances will be equal. Defining it as a rectangular, the two sides at the least will be equal, and if we are defining it for the quadrilateral, then all the sides need to be equal. We have got one question where these charges are in a configuration of square, so we are not doing in the configuration of square. We will do it just for a quadrilateral where we do not know the exact distance of the sides of this quadrilateral. So our quadrilateral can go like this. Okay, quadrilateral can be anything. It looks like a trapezium. Let's take some little like irregular kind of surface so that it is easier for one to understand. Again it comes, so let's make anything, and we need to bring the charges in such a configuration that all charges are bound here: q1, q2, q3, q4. These charges are present at a position vector of r1, r2, r3 and r4. Now we'll go step by step in this. Our step 1 is to bring charge q1 from infinity to r1 position, and to do so, potential it created is equal to kq1 upon r1 from the infinity, and work done in doing so is 0. So this is our equation 1. Now we have step 2. In this step 2 we are bringing q2 from infinity when q1 is present at r1. So the potential because of q2 will be kq2 upon r2p, but the work done will be equal to q2 into potential due to 1 at r2, which will give us kq1 q2 upon r12. This is our second step and second equation. Then it comes to step number 3, where we have a charge q3 coming from infinity to position vector of r3 when already q2 and q1 are present at r2 position vector and r1 position vector respectively. Okay, so the potential due to q3 that is created equals to kq3 upon r3 from the position of p, and the work done will be given as q3 into v1 at r3 plus v2 at r3, and it is equals to k into q3 q1 upon r13 plus k into q3 into q2 upon r23. So this is the third equation. We will go for the step number 4, where we brought q charge from infinity to r4 position vector when q1, q2 and q3 are at r1, r2 and r3 respectively. So the potential that's generated due to charge 4 is k q4 upon r4p, and the work done will be given as q4 into v1 at r4 plus v2 at r4 plus v3 at r4. So we know v1, v2, v3. See the above equations. So the work done we find is k q1 q4 upon r14 plus k q2 q3 upon q2 q4 upon r24 plus k q3 into q4 upon r34. So that is the equation number 3. Now in the given quadrilateral system, in the given 4 charge system, we aim at finding the total work done in bringing in bringing the charges Q1, Q2, Q3 and Q4 to the required configuration, So it will come W total equals to W in the step 1, step 2, step 3 and step 4. Step 1 is 0 plus step 2 is KQ1 Q2 upon R12 plus step 3 is KQ1 Q3 upon R13 plus K Q2 Q3 upon R23 plus K Q1 Q4 upon R14 plus K Q2 Q4 upon R24 plus K Q3 Q4 upon R34. So see over here, this comes from the equation number 4. This is not equation number 3, this is 4. This comes from the equation number 3, this comes from the equation number 2 and this comes from the equation number 1. 1, 2, 3 and 4. So after that, taking the common out, common is just K, nothing else, K out, what we get is Q1 Q2 upon R12 plus Q1 Q3 upon R13 plus Q2 Q3 upon R23 plus Q1 Q4 upon R14 plus Q2 Q4 upon R24 plus Q3 Q4 upon R34. So this is the total work done in a system where we have considered the 4 charges. Now in case these R1, R2, R12, R13, R23, R14, these distances are same. We are considering a square. What will happen? All these distances will become same. And then we are considering what? We are considering the charges Q1, Q2, Q3, Q4 all equal. How much amount of work we will be doing at the end? Let's just do one little calculation for it also. Now in case what happens is that our charge Q1 equals to Q2 equals to Q3 equals to Q4 and our distance R12 equals to R13 equals to R14, like it makes a square, and then here 1 2 3 4, from 1 to 2 equals to 2 to 3 equals to 2 4 equals to 4 1 comes, right? And then 1 to 3 equals to 2 to 4 charges distance, so that will come around, it will come as R and it will come as R under root 2. So if we are defining in such a way, what exactly we got in the previous slide was work done equals to some amount of values, right? It was like K for the first case Q1 Q2 upon R12, for the other case Q1 Q3, for the other case Q2 Q3 as R13 R23, then Q1 Q4 Q2 Q4 Q3 Q4. These are the other values which we have received as 1 4 2 4 and 3 4. These are the distances. Now we have seen this distance is equal to R. 1 3 is R by 2. I'll mark it with the red. These values with the red. 1 3. Then 2 3 is different. 1 4 is different. 2 4. 2 4 is this, right? And these are R. Now substituting it, and we have managed to say that Q1, Q2, Q3 everything is same. So exactly what we will be getting is over here is W equals to K. This will become Q square, Q square. This will also become Q square, Q square, Q square, Q square. As these are same, so all the Q squares will come out, Q square into 1, 2, 3, 4. 4 will become R, 1 upon R plus 2 upon R under root 2. 2, these are two values. R13 equals to R24 equals to R under root 2. These are diagonals. These are diagonals. So that's why, see here, 1, 2, 3, 4. This is R. So what about this? This will be R under root 2. Similarly, what about this? This will be R under root 2. That's what the concept we have taken here. Now we will take 2kq square upon R, as the common left is 2 plus 1 by root 2. For a square, this is the amount done. If we are considering our quadrilateral to be a square and all the charges have same magnitude, in that case amount of work done is given by above equation. I just hope that you have understood the concept of the electrostatic potential which we determine for a given of system of charges. We can extend it little bit more to understand the charges for like n number of charges also, but that is beyond our syllabus. We do not need to study. Only the 4 charge system, up to 4 charge system is in our textbook, is in our syllabus, which we need to understand and read. So we have done in today's class is 2 charges, 3 charges as well as 4 charges. In the 4 charges we have seen a common example of square. Also. So this will help you further for your classes as well as for your examination. I hope you understood it well. That's all for today's class. We'll meet up in the next class with a new topic. Have a good day.